Hello, pre-cal students. Today we will be going over Unit 9 Notes Day 3. I highly recommend you use a writing instrument that you will be able to erase. Did I say that right? Make sure you use a writing instrument that erases. There you go. You mean what I know. Let's get started. Okay, jargon. Feel free to read all that. If it makes sense to you, great. If not, don't worry. I will explain it all as we go. Example 1. Identify whether each function has an odd/even degree and a positive or negative leading coefficient. All right, well, let's take a look at this end behavior. End behavior, think of it as which direction are these arrows going? So this graph is trending on the left side of the graph down. On the right side of the graph, it's trending up. So its end behavior is down, up from left to right. You see how these are opposite arrows? Anytime your arrows are going opposite directions, your degree is going to be odd. Think odd, opposite, odd, opposite. Now, anytime your last arrow is trending towards positive infinity, then that means your leading coefficient must be positive. Now we can do our end behavior. As x approaches negative infinity, f of x approaches, what's our first arrow doing? It's pointed down, so negative infinity. Over here, as x approaches positive infinity, f of x approaches, what is our second arrow doing? It's pointed up, positive infinity. Okay, over here, notice our two arrows from left to right are pointed up, up. Anytime they are going the same direction, you're dealing with an even degree. Leading coefficient, well, let's look at the last arrow here. That last arrow is pointed up, so we must have a positive leading coefficient. As x approaches negative infinity, f of x approaches, what is the first arrow doing? It's going up, so positive infinity. As x approaches positive infinity, f of x approaches, what's the last arrow doing? Also pointed up, so positive infinity. Okay, looking at this graph from left to right, it looks like our left arrow is pointed up and our last arrow is pointed down. They're going opposite directions, so the degree is odd, odd, opposite, odd, opposite. Leading coefficient, well, the last arrow is pointed down or towards negative infinity, so our leading coefficient must be negative. All right, here we go. As x approaches negative infinity, f of x approaches, what is the first arrow doing? It's approaching positive infinity. As x approaches positive infinity, f of x approaches, what is the last arrow doing? It's pointed down. So negative infinity. End behavior, you're welcome. Now we're on to side 2. Read over that. Do what you want with it. I'll explain it as we go. Example 2. Fill in the chart for the graph. So what are the factors of this graph? Here's what we're looking for. We are looking for, where does the graph touch the x-axis? Here and here. So these factors are x minus 2. This factor is x minus 2. This one is x minus 4. Now, take a look at the graph. You see how this one is approaching positive 2 and then it bounces off? That means it has a multiplicity of 2. That factor has a multiplicity of 2. Anytime it approaches and bounces, we know that we have a factor that's being squared. Now, this one here, notice that when it's approaching 4, it begins to flatten out. See that? It's flattening out. Anytime you see that pattern, that means it must be cubed. So a cube equals flattening out. Zeros, if we were to set each of these equal to 0 and solve, we would get 2 and we would get 4. Those are our x-intercepts, 2 and 4. Multiplicity, look at the exponent of the factor. We have a multiplicity of 2. Multiplicity, what is the exponent of this factor? 3. Now, what is the meaning of the multiplicity? If we have a factor that's being squared, it's going to bounce at the x-axis. If we have a factor that's being cubed, it has a multiplicity of 3, that means it is going to flatten out as it approaches the x-axis. In behavior, let's take a look at our arrows here. Looks like from left to right, if I were to draw arrows on this graph, down, up, down, up. So as x approaches negative infinity, f of x approaches first arrow, negative infinity. As x approaches positive infinity, f of x approaches the second arrow, positive infinity. F of x equals. Now what they want us to do is they want us to write what this equation could look like, assume that we don't have any stretch or compression. That's what a equals 1 means. Well, we already have it in factored form. We pretty much have already done it. Just keep your factors and their multiplicities. And example 2 is now done. All right, example 3, given f of x is equal to x plus 2 squared and x minus 3 cubed, let's figure out the characteristics and features of this graph. Well, let's think, they want us to do in behavior. Now remember, the rule of exponents, when we're multiplying exponents, we're really adding them. So I see an exponent of 2, I see an exponent of 3, 2 plus 3 is 5. Therefore, this is an odd degree polynomial. Our arrows are either going up, down, or I said up, down. They're either going down, up, or up, down. The way that we now can determine, well, which one is it is, well, is our leading coefficient positive or negative? If we were to multiply all of this, and notice your x's are positive. Notice that in front of the parentheses, there's no negative. In this case, we would have a positive leading coefficient. Therefore, our last arrow must be trending towards positive infinity. So this is our end behavior here. So here we would write negative infinity. Here we would write positive infinity. Now, maximum number of turns. Here's how you can determine that. Whatever degree exponent you're dealing with, we've already determined that this is a 5th degree. Remember, we added 2 plus 3 to get 5. Whatever your degree exponent is, just subtract 1 from it, and that will give you the maximum number of possible turns. It doesn't necessarily mean you're going to have that many turns. It just means that's the maximum that you're going to have. Fill in the chart, factors. Well, it has given us the factors. Zeros. If we were to set these equal to 0 and solve, we'd get -2, +3. Multiplicity. Well, what is the exponent of the factor? It's a square. So we have a multiplicity of 2. Here we have a multiplicity of 3. What is the meaning of this multiplicity? What this means is, as our graph approaches -2, it's going to bounce. Here, the meaning of a cube, a multiplicity of 3, means as it approaches that x-intercept, it will flatten out. Now, here is where having something that erases is going to come in handy. If it wants you to sketch the graph, these can be a little tricky. Here's how I like to do them. I like to think about, well, what are my x-intercepts first? I know I have one at -2 and 3. So I'm going to plot those first. Here's -2. And then 1, 2, 3 here. Now, remember, one of the intercepts, we're going to have a bounce. The other one, we're going to have a flatten out. So what I do is at -2, which is here, I'm just going to write myself a B, knowing I've got to bounce at that point. Now, where x is 3, it has to flatten out. So where x is going to be 3, I'm just going to write an F, letting me know I need to flatten out at that point. Now, something else that you want to take into account is, well, what would the y-intercept be? In order to find the y-intercept, you would plug in a 0 here and here, and then solve. Well, 0 plus 2 is 2. Don't forget, we have to square that. X minus 3, I'm sorry, 0 minus 3 is -3. Don't forget, we need to cube that. If we were to take 2 and then square it, we would get 4. If we were to take -3 and cube that, we would get -27. So now we have 4 times -27. That is going to produce a y-intercept that's negative and way down here. Don't worry about it being accurate, okay? I just know that I'm going to have a y-intercept that's negative. That's the most important part. Is your y-intercept negative or positive or going through the origin? So we know our y-intercept is negative. Okay, then what I like to do is I like to think about my end behavior. Remember, our end behavior, we have arrows that are pointed down and then up. So I like to do this, down, up. And then now we're going to start sketching. So I'm going to approach the B, bounce, go through the y-intercept, make a turn, approach that F there, flatten out, and then hit my arrow. Let's now go on to the next side. For example 4 and 5, we're going to need to sketch the following. So let's see here, it's in factored form, so it's very easy to identify your x-intercept. We're going to have an x-intercept at 3. Notice that its multiplicity is 2, so it should bounce at 3. Here we are going to have an x-intercept at -1. Now notice the multiplicity, well, we don't see an exponent, so we could say it has a multiplicity of 1. And what that means is it's going to cut straight through. It's going to go right through that point. It's not going to bounce. It's not going to flatten. It's going to go right through or cut. That's what we refer to it as. And then we have another x-intercept at -5. So here was -1, -2, -3, -4, -5. It is being cubed. So we have a multiplicity of 3. So we should flatten out at that point. Now let's take a look at, well, what degree polynomial are we dealing with here? We have an exponent of 2. We have an exponent of 1. And an exponent of 3. So we need to add those together. 2 plus 1 plus 3, so 3, 4, 5, 6. This is a 6th degree polynomial. Do you remember how many maximum number of terms it should have? 6 minus 1 is 5. Since this is a 6th degree polynomial, that means our end behavior is going to be going the exact same direction, either up, up, or down, down, depending on the leading coefficient. Well, let's take a look. All of your x values are positive, and if we look in front of the parentheses, that is positive also. So this is going to be our end behavior. So I'm going to go ahead and draw an arrow here and there. And now let's take a look at, well, what would our y-intercept be? Would it be negative or would it be positive? If we plugged in a 0 here, 0 minus 3 is -3. And then if we squared that, it would be a +9. Well, all of these other numbers are positive, so we would be multiplying 3 positive numbers together, meaning our y-intercept is going to be positive. So our y-intercept, we could just say, is here. Okay, so let's go. I'm going to approach the first x-intercept where I see that F and then flatten out. And then I need to turn, cut through that intercept. I've now hit the y-intercept. Let's now approach that letter B, bounce, and then connect with that arrow there. And that one's done.
Example 5. This one is probably the most confusing one. Let me go ahead and give you a little tip here. You see how we have a negative x? It could be a negative x or a positive x, but you see how we have it in front of all
These parentheses here? That tells us that we're going to have a y-intercept of 0. Anytime you have an x or a negative x in front of all your sets of parentheses, your y-intercept is going to be 0. You see how we have a negative in front of this set of parentheses, and all of these x values are positive thereafter? That means our leading coefficient is going to be negative. Leading coefficient is negative. Okay, now let's take a look at our multiplicity. I see an exponent of 2, an exponent of 2, an exponent of 3, and then this has an exponent of 1. 2 plus 2 is 4, 4 plus 3 is 7, 7 plus 1 is 8. So we are dealing with an even degree polynomial. So same exact end behavior, either up, up, or down, down. The leading coefficient will now narrow it to which one it is. So it's got to be this one. This is our end behavior here. Okay, starting from left to right, what are our x-intercepts going to be? Well, we're going to have one at 0. I just told you that if we see an x that is in front of our sets of parentheses, that we're going to have a y-intercept at 0. So we will be having an intercept at 0. Since it has a multiplicity of 1, it is going to cut through that point. Here we have an x-intercept at 4. 1, 2, 3, 4. Its multiplicity is 3, so we will flatten out at 4. Here we have an x-intercept at -2, -1, -2. It has a multiplicity of 2, therefore it is going to bounce at -2. And then here we have we have an x-intercept at -5. It has a multiplicity of 2, so it's going to bounce at -5. In behavior is down, down. So let me draw my arrows down, down. Now hold your breath. Let's do this. Let's approach the letter B, bounce. Approach the next letter B, bounce, turn, cut through, approach the letter F, flatten, and then connect with your arrow. Woohoo! We did it. Example 6, write an equation and sketch. Give me a second. Okay, yeah. I'm not going to sketch any of these. I think you get the point. The most important part of this particular section is if they give you a set of zeros, roots, whatever leading coefficient, could you then write the function? So let's begin with y equals. Could you write the equation? Roots, we have a single root at 5. So that means multiplicity 1 at 5. So x minus 5 in parentheses with no visible exponent. We have a triple root at -2. So the x-intercept is -2. So in factored form, it would be x plus 2. And since it's a triple root, that means it has a multiplicity of 3. And a single root at 0, meaning in the very front of our parentheses, there is an x. Single root, multiplicity of 1. The leading coefficient is negative. Boom, put a negative in front of the x, and you're done with that one. For example 7, notice what I've crossed out there. I don't want you to worry about that. I want you to just be more aware of, can you write a function if it's written like this? You're not going to need to know about lying above the x-axis between -3 and 1. Don't worry about that. Just this is the basic that you're going to need to know here. So 7 cuts straight through the x-axis at -3, -1, and 1. So we have a intercept at -3 in factored form, x plus 3. We have an x-intercept at -1, so in factored form, x plus 1. And then we have an x-intercept at 1, so in factored form, that's x minus 1. Since it cuts straight through every single one of those, we have a multiplicity of 1. That's it.
Example 8, please take notice of what I don't want you to stress out about. And the highlighted portion is what I do want you to not stress about, but just become familiar with. Next, let's do it. Touches the x-axis at 0, touches the x-axis at 0, and cuts straight through the x-axis at 2. This should be a degree of 3. This should be a third degree polynomial. So y equals touches the x-axis at 0. So what that means is in the very front, since we have an x-intercept at 0, we should see an x. Now it tells us it touches it. It doesn't go through, it doesn't cut, it doesn't flatten, it touches it and then bounces off. So this one's squared. Next, cut straight through the x-axis at 2. The x-intercept is 2. So then factored form, that would be x minus 2. And since it cuts straight through that point, we have a multiplicity of 1. The 1 is not needed, but this should be a third degree polynomial, and 2 plus 1 is 3. A equals plus or minus 1. So we shan't be assuming that. Let's begin with y equals. Let's take a look at what this x-intercept is. That x-intercept is -3, but in factored form, that would be x plus 3. And then take a note, what is it doing once it gets to -3? It's bouncing, so it has a multiplicity of 2.
We have an x-intercept there at the origin. So what that means is we have an x in front of all these parentheses, and then notice it begins to flatten out at that point. So it must have a multiplicity of 3. And then we have another x-intercept here, where x is 6, so in factored form, that would be x minus 6. It is cutting through that point, therefore we have a multiplicity of 1. Okay, it has given us the coordinate -2, 2. So we want x to be -2 and y to be +2. What we don't know is what is a. And the a value would be here in front of the x cubed. So we're going to substitute what we know so that we can figure out what we don't know, which is a. So we want y to be 2. We want x to be -2. And then we're going to start simplifying. You know what I did? I forgot to plug in what did I forget to plug in there? A -2. Give me just a second. I'm actually glad that I did that because this is a good opportunity for me to tell you what the most difficult part of these problems are. Just remembering that there's so many steps that are involved. So take your time and check to see if you've got everything plugged in correctly. So everywhere there was an x, there should be a -2. And where we see a y, there should be a 2. Cube, cube, square, square. Okay, let's go. Oh, here we have a -2 cubed is -8. Here we have -2 plus 3, which is 1, and 1 squared is still 1. -2 minus 6 is -8. All right, now here we have -8 times 1 times -8, which is going to be +64. Now, another way of writing this, and what you're more familiar with, would be 2 equals 64a. This is a times 64 or 64a. So now we can divide both sides by 64. A equals 1/32. That's our a value. So now we can write our final answer, which would be this. I'm done. Okay, truth be told, I am running out of time. I'm not going to do that one. If you really want to see that one done, stop by room 402. I'll show you. Let's go ahead and go to the back. A lot of notes on today's lesson. Okay, example 11. Given this function, find the following graph. Find the following and graph, but factor first. So let's make sure and do that. I'm going to make this a little bit bigger. I just like drawing bigger. Okay, we have 1, 2, 3, 4 terms. Usually, that's a hint that they want you to factor by grouping. Out of this group, we could factor out an x squared, leaving us with x plus 3. Here, we would want to take note first, we're separated by a minus sign, so we'll include that. The only thing that we could factor out would be a 1, or -1 more accurately, and that would leave us with x plus 3. So our factors are x squared minus 1, x plus 3, but wait, that is a difference of perfect squares. It can factor more. Difference of perfect squares, so give your new parentheses different signs. The square root of x squared is x. The square root of 1 is 1. And now it's fully factored, and I'll write that up above here. Y equals 1 x plus 3. All right. In behavior, well, it looks like all of these have a multiplicity of 1. 1 plus 1 plus 1 is 3. So this is an odd degree polynomial. So opposite in behavior, the leading coefficient is positive. All of these x values are positive. So it must be down, up, or negative infinity, positive infinity. Maximum number of turning points. This is a 1, 2, third degree polynomial. 3 minus 1 is 2. Take your degree, subtract it from 1. That's the maximum number of turns. F of 0. Everywhere we see an x, you plug in a 0, or you could just do it here. I prefer this one. Because if I plugged in a 0 here, 0 cubed is 0, plus 3 times 0 squared is 0, minus x, or sorry, minus 0 is 0. The only thing we're left with is negative 3. So f of 0 is negative 3. What are the zeros? Look at your factors. Keep the numbers, reverse the signs. So negative 1, positive 1, negative 3. We have a multiplicity of, what is it, 1 here? Oh, we want a multiplicity of 1 for each of these zeros. There's a multiplicity of 1. All right, so let's now graph. We have an x-intercept at negative 1. We're going to cut through that point. We have an x-intercept at positive 1. We're going to cut through that point. And then we have an x-intercept at negative 3. We will cut through that point also. And we know that our y-intercept is negative 3. So right about there. Draw your arrows. And let's go. Cut. Cut. Boom. That one's done. Whoa, I was recording that whole time. And we're back. Example 12. Find the following using your calculator. Why does it want to use us to use our calculator? I don't know. We're about to find out. Wait, where is my calculator? Alakazam. Poof, there it is. Bet you didn't know I knew magic. Let's get started. Let's plug this into our calculator. First step, most important, make sure it's turned on. Go to y equals, clear out any previous data, and then let's start entering in this polynomial. Graph. Interesting. Okay. In behavior. Well, notice if we were to draw an arrow there and there, we would be down, up, down, negative infinity, up, positive infinity. Maximum number of turns. Well, this is a third degree polynomial. 3 minus 1 is 2. Maximum or minimum value. Now I see why it wants us to why it wants us to use our calculators. So we have a maximum value here where we see a peak and a minimum value there where we see a valley. So let's figure out what is the maximum value first. So second trace, we need option maximum. And then now here's our maximum. What are the x-intercepts that are, see, like, if I were to like to do an axis of symmetry here, right there, where does this graph cross the x-axis? Left and right of that axis of symmetry, here and here. So I want to use those x-intercepts. Looks like we have an x-intercept of -1, -2, -3, -4, and -1. So -4, enter, -1, enter, enter. So this is our maximum value right there. We're going to have a maximum at 9.209. Now let's go locate this minimum value. All right, now this minimum value, it looks like it's at, if I were to draw an axis of symmetry, it looks like it'd be at x equals 0. So then what are the x-intercepts that this graph produces that are to the left and the right of 0? -1 and +1. So second trace, minimum. Let's do -1, enter, 1, enter, enter. So we have a minimum value at -3.061, looks like. F of 0, if we took a 0 and substituted it everywhere we saw an X, we would be left with -3. What are the zeros of this function? Let's see if we can just use our table.
Tartar sauce.
We can't. Okay, graph. So we're gonna have to use our trace feature here, which is why they wanted us to use our graphing calculator. This x-intercept looks like it's going through -1, -2, -3, -4. I want you to think about a number line. Which numbers come before and after -4 on the number line? That would be -5 and -3. So those are the values we want to use to solve this. Second trace, option 0, and then -5, enter, -3, enter, enter. Looks like we have a 0 at -4.064. Yep. Now let's find this 0 here. Second trace, 0. It looks like that x-intercept is -1. So on the number line, what comes before and after -1? That would be -2 and 0. So that's what we want to use. -2, enter, 0, enter, enter. Looks like our other 0 is at -0.828. And then our last x-intercept looks like it's going through 1. So think about a number line. What comes before and after 1? 0 and 2. Second trace, option 0, 0, enter, 2, enter, enter. We have another x-intercept at 0.892. We have a multiplicity of, I'm sorry, nope, disregard that. Looking at the x-intercepts, the zeros, we are cutting through every single one of those. So these have a multiplicity of 1. Sorry for the confusion. I was thinking about something else. If we had to graph this, so doesn't it look like something like that? I mean, come on, it's right there. That doesn't matter so much. Have a good day.